Hey guys, so today we're going to go over the concept of happy number, which is the new topic in Algos and 10. This is also a great usage of a divide and conquer. This concludes part 1 of Algos and 10. Part 2 will have the data structures of basically trees, medians and medians, hashing tables, and a good old hashing set with some pretty cool applications. Also, since it's my birthday coming up, we're going to have a very interesting birthday problem as well regards to Algos and 10 coming up on my birthday on August 6th. Let's get down to business and let's try to make some numbers really, really happy. By the way, the happy numbers is a LeetCode problem, but I modified it for my own personal benefit. Of course, if you want to make the numbers happy and yourself happy, make sure to subscribe to my channel. So this number problem will have a little bit of modulo in it, which will show you that it's going to be a pretty quick algorithm, actually linear time. Also, you can see I've been working on some emoji drawing in terms of my subscribes as well. In terms of general problems for Algos and 10, I noticed that some of the problems were taking a little too long, so I'm going to try to shorten up today to basically be no more than 15 minutes total. So let's define what is a happy number. So a happy number, n, has the following. So n can only be in the range of 1 to n to 2 to 32 minus 1, because we're trying to keep basically n in the integer range. In addition, the property of n is as follows. That basically the sum, which is the biggest n can be, is equal to m from I to m of n of m cubed, which is equal to the sum, which is the biggest n can be. So sum of its digits, basically. So you're given a number n and m digits for n. Let's say as a quick example, n equals 1, 2, and 3. So what does that mean? It has 1 cubed plus 2 cubed plus 3 cubed, which is 1 plus 8 plus 27, which is 36. So let's do the test. Is 123 divisible by 36? And our answer is no. So this is not a happy number. So let's find an example that is going to give a happy number, which hopefully you already know what the number is going to be. I'll give you a hint. It's actually very close to 123. It's 27. Okay, let's give 27 a shot. So it's 2 cubed plus 7 cubed, which is 343 plus 8, 351. So is 351 divisible by 27? And the answer is obviously yes, it's 13. So that is great. So n equals 351 is a happy number. So now let's use the divide and conquer algorithm to determine if an arbitrary number n is considered a happy number. So yes, the second constraint is the following for the problem set. So basically have a case where you have the number n equals the largest of its digits, which is pretty cool. So that means you have, for example, you have the digits of n1 to nm for m digits. That's the second constraint. Of course, m can be at least 1 up to basically the len of how much n is as a string. So if you turn this into a string, that's what happens. That's where LeetCode string operations come in. So also, we want to make sure you have also another constraint for each digit I. So for each, this is the mathy symbol for each digit I in m. We basically determine that n of I cannot be any more than 2 to 32 minus 1. And that's the second constraint. So let me now show you the quick divide step. So the divide step is pretty easy in this problem. You have basically an array where you store the digits, 1, 2, 3, 4, right? And then within the array, you have, for example, n equals 1, 2, 3, 4. So you just put in 1, 2, 3, 4 as each part of the array up to m digits because of the problem's restriction. And this is the first part of the divide step. We essentially partition n into n1 nm total amount of digits. And that's it for the divide step. Pretty easy. This is one of the easiest divide steps in all of Algos of 10. So if you don't understand this step, you would probably want to review first grade elementary math, because it's literally ones place, tens place, hundreds place, all that other good stuff. The conquer step, though, gets a little more interesting. This one gets a little bit more mathy, so start getting into some more data structures like hashing. For the conquer step, we basically say the following. For each number digit, ni from 0 to ni to 2 to 32 minus 1, actually sorry, from 1. 1 to ni to the 232 minus 1, we first do the following. We do ni modulo equal 10. The reason why we do modulo equal 10 is for the version of what we call the dividend, or the dividend, depends on how you want to pronounce it, the dividend of the division. Then we divide by 10. This is called the difference between integer and float division. We always want to choose integer division because we're working with integers here. Float division, for example, in Python 3, is a little bit different. That's something we'll deal with more advanced in another Algos in 10 problem set. Then finally, we calculate the sum to be equal to ni mod 10, right? And we take that to the power of 3. And the reason why is because of that formula again, m to sum of I equals 1, n to the m cubed has to equal sum. So these are related. These are called related formulas. This is getting a little bit mathy, I'm sorry, but this is where things get a little bit mathy. Also, we ensure, very important, that there actually exists a ni that eventually equals to the largest digit, or the max of n1 to nm. And that's it for the mathy version of the conquer step. So now I'm going to show you the very interesting way to merge all this. Alright, to merge we're going to use something called a hash set data structure, which is an interesting data structure. So a hash set, you have two main functions. You have a put and a get. So for the divide step, we basically recursively, for the combine step, we basically recursively, basically recursively repeat the conquer step until n equals the largest sum, so max of n1 to nm. So for example, we have originally n equals to 93. We basically have n equals to 9 in the end of the algorithm. So here's the following case. In first case, if we find the sum to be in the hash set, let's say hs of n as a function for the hash set, hs of n, then we basically return false, because you do not want that to be in there. You don't want duplicate hash set, and you want to append the sum. So add the sum to the final array. However, if the sum is not yet in the hashing set h of s of n, then it is true and you are done with the algorithm. So you're done with the algorithm, and that is how you basically combine and merge. So this will obviously result in what we call the happy true-false return array. And that will basically determine whether the number is actually happy or unhappy. So as a quick example, you can try n equals 93 just to convince yourself that this algorithm works. But I'm going to now show you the really quick runtime solution. So here is the runtime solution, basically. So runtime, you have the following. You have O of 1 to basically calculate the sum equals, you know by now what the formula is, up to m, the sum of each digit, cubed. You have O1 again to calculate if the number is happy or not. That's basically just the sum of cubes. Then you have O1 again, so you can see how repetitive this is. O1 for basically the ni mod 10 and the ni divide by 10. But finally, you just have O of m for the hash set because you want to do it, the true false, for up to the m digits in n. So your total runtime is O of m in terms of time. And in terms of space, it's going to be O1 because of hash set. And that is it. That is your algorithm. So you can see this is the most efficient way to ever do the LeetCode problem happy number, if you ever get it. So now let me just quickly introduce what's coming up next. So we have something called the AA tree, the median of medians, a hashing set, and also the Dijkstra modified cyclic graph. I will show you the links in the comment section or in the video description just to give a little preview what the problems will be. And those videos will all be coming out simultaneously on one day right before my birthday. So this is Jason Liu, Algos in 10 episode 5, happy numbers, and have a happy and nice day.